Okay, so I'm going to talk today about a theorem prover for doing arithmetic in Metamath. Now, if you were here on Wednesday, you've already seen this slide. So Metamath, basically a computer language for representing proofs, simple verifier. We have a few verifiers and proof assistants. For a little bit of comparison with Isabel, since we heard some numbers a few days ago, the main set theory database has 25,000 proofs instead of 65,000, and it's about 500,000 lines of code, and the file is about 24 megabytes. So it's significant. So here's a little information on the Metamath 100 project, which is a project to prove these formalizing 100 theorems. So this is a great way to get a bunch of interesting facts on diverse fields, because the 100 theorems are all over the place in terms of the libraries which they pull from. So here's a list of all the things which are new just since last year. A year ago I had a similar list like this when I presented most of the theorems which had been proved. And it was about this long, but that was since the beginning of time, and now this is just in the last year we've managed to prove all of these theorems. And so here's a little bit of a plot of showing how there's recently been a big explosion in the amount of proofs we have. And so here I've highlighted a few particular ones: Bertrand's postulate, the birthday problem, and the cubic and quartic formulas, which rely directly on what I'm going to present here in this talk.
Actually, we're now at over 60, but it's like Vida keeps dragging his feet and doesn't put those in.
Well, I'll keep closing in on you. All right. So, so how does Metamath work? You have a theorem or axiom, which is a list of hypotheses, and then a conclusion. Each of those is a formula containing constants and variable symbols. The variables are meta variables, which I'm not going to go too much into detail on what it is. We can talk about it offline if you like. But basically they can substitute for, like, these are well-formed formula meta variables, so you can put any well-formed formula which would contain more meta variables if you like. So definitions and axioms are treated as exactly the same. We have a separate utility, not part of the main Metamath checker, which can check definitions for conservativity using a simple checklist of things which we know ensure conservativity. So in particular, when we're dealing with constant symbols for numbers, for instance, you have to define two. Two is a token, just like any, you have strings and they represent whatever you define them to mean, and so you have to define 2 equals 1 plus 1. Now, of course, you can't do that for all the thousands and thousands of numbers which you can fit in a string, so that would be kind of annoying. So we have to find a better way to do that. So here it's saying again, a number like 999 is not going to be in the database. You can define it. You might not define it as 999 even. So it would be problematic to rely on a system like that. It is possible, though, to define arbitrary syntax. So this here, you could define implication, and this is how implication is defined: it's a well-formed formula which is dependent on two well-formed formulas here, phi and psi. We do need no ambiguity in the language for parsing to work correctly. We can't check ambiguity, unfortunately, because that's an NP complete problem or something. So, but we do know that prefix syntax is always going to be unambiguous. So this is a nice way for us to construct very, if we need some sort of complicated expression, we can just make it if we put some special thing at the beginning, then we can already be guaranteed that it's not going to cause any problems with ambiguity with the rest of the language. So here let me quickly state what Bertrand's postulate is. It says there's a prime between n and 2n. It's very convenient, easy to state, and really hard to prove. Erdos proof has this, it generally starts, you assume n is greater than 4,000, okay? So you do some work and you can show that for large enough n, you can prove it, but that's a lot of base cases. We still have 4,000 cases left to prove. So the usual way you do it is, here's a nice sequence of things which I claim are primes. And, well, how do I know they're prime? Well, how do you prove a number is prime? You can use trial division. For the larger numbers, you can also use Pocklington's theorem. And thank you, Mizar, for informing me about Pocklington's theorem. I'd never heard of it before I checked Mizar's formalization of this result. So there it is. So we need a way, so Pocklington's theorem in particular requires modular exponentiation. So there's going to be a lot of multiplication involved. And so we need a good way to handle arithmetic on large numbers, where large means like 4 digits.
But surely it doesn't take that long to try all the divisors of a number with 4 digits. So Pocklington seems a bit going over the top of those numbers.
In hindsight, we probably could have done trial division for those numbers as well. We would have had to prove a few more primes along the way. Currently we're actually not even using the proof that, we have a proof that 4001 is prime, and it's a very nice reference for how to use these things. But actually it's not used in Bertrand's postulate proof anymore because we managed to find another way such that the proof starts let n be greater than 64. So now we don't even need these giant numbers. So it kind of defeated the purpose in the end for this original work. But then again, now we have a great system. So, So we're going to define the decimal operator here. It's just denoted by a semicolon. As you can see, it's a prefix operator, which is why, again, we can be sure that this is not going to cause any ambiguities in the language. Here's a few examples of 13 and 269 being represented as using this notation for decimal numbers. There are actually spaces between these so that it parses correctly. If you read the associated paper, it talks about base 4. The original version of this was implemented in base 4, but afterwards we went through and changed it to base 10. It was mainly because it was easy to get it up and running quickly in base 4 the way we had the system at the time. So this structures a decimal number as a Lisp sort of list. You have you have the lowest digit, and then you have everything bigger. And so you can, you can represent 10 in 2 representations because this is a 2-symbol token, and there's also this way, but that's not all that important. So, so these are going to be the building blocks of our algorithm. So we have lots of theorems along this line. So this allows us to iterate over the shape of the expression. We want to show that m plus n is equal to this decimal, and so we break it up into its low digit, prove that, break it up into its high digit, prove that, which will recursively use the same theorem again and again. And then we have the similar things for multiplication. Here's some examples of individual addition facts which you need at the base case step. Commutativity, because we only do it for the larger number is going to be on the left, and then you can use commutativity to get the other one. And then less than. So this is implemented for addition, multiplication, and less than, and that is actually good enough to get pretty much everything else you need. You just put it into the form where those 3 operations will do the job. So yeah, we can recurse over the list structure of a term. You can also implement algorithms like Karatsev multiplication. I tried doing that out yesterday, and it works just as well, although it's actually not I mean, in most of the cases which we're dealing with, it's much less efficient than just straight multiplication. But this is really just showing that you can implement all of these algorithms in the same order which you would expect from regular computer science. They say that you can do these grade school multiplication algorithms in O of n squared, and yeah, we can produce proofs in steps of O of n squared. You can store lots of types of structures this way, not just numbers. You can store graphs and other things as lists or as trees, and you can iterate over them. So this really has a lot of abilities to mimic most of the aspects of programming, even though it's a proof and it's just recursive applications of these theorems. These proofs are designed so that they always return the same thing, which, I mean, I should say if you want to prove, say, that 6 times 6 is 36, you're always going to prove it the same way, probably by referring to a theorem which says that, if there is one, or else you can apply an algorithm, and if you found the minimal proof for it, is always going to be the minimal proof for that particular fact. So this allows for a nice recursive structure for proving a given arithmetic fact. You just find you iterate over the different shapes which you can have on the expression you want to evaluate, and then prove the sub-goals which you get as a result. In the evaluation in the Mathematica program, which we use to implement this algorithm, we can evaluate terms. This is just a matter of putting the terms together and using the native language interpretation of what these terms mean, so that we can create the subterms, like let's go back a little bit. So sometimes you have to know intermediate steps, like here I wanted to know that this times this is CD, and we're going to need to know what this E is later. And I can do that just by figuring out I break up N into its low piece and use P, multiply them together, and that gives me an expression, and I can break off the high and low parts and turn that back into an expression for Metamath consumption. So here's an example of an actual proof which is done by this algorithm. So we're trying to prove here that 2 to the power of 8 is 256, which quickly reduces to 16 times 16 is 256. And then we're just applying these rules over and over again. We have multiplication, breaking up on the left, breaking up on the right, and then commutativity and base rules. And so you just get all these rules together and you end up with a direct proof in Z of C and all that. And this is considered a relatively short proof. It's only 7 lines in the compressed representation, which we usually use in a .mm file. So limitations. So this is a limited domain theorem prover. It can prove any true statement about integers and addition, multiplication, the decimal operator, and less than, as well as proving many of the closure. You have to show closure for everything, so it can prove closure in the positive integers, non-negative integers, and complexes, and it wouldn't be hard to extend that with other kinds of closure as well. You can also extend this to exponentiation. If you look back here, it's actually using this num-exp theorem at the very beginning, which is going to be used to break down a exponentiation into, I guess it's referring back to exponentiation of 4. And so it's going to use exponentiation of 4 plus 4 in order to turn this into 16 times 16. So you can use little extensions like that to the arithmetic engine in order to handle modulo and other sorts of operators like that. So pretty much all numerical theorems which you want to deal with, comparison of fractions and these other things where you really have concrete numbers and you just want to add them together, you can always reduce this down to addition and multiplication of positive reals. So this is, or of positive integers, I should say, or non-negative integers. So this is not a big restriction. We can pretty much put everything in this form and then just throw the engine at it and let it prove all these sub-goals. The first version was created for Bertrand's postulate, and it succeeded. It managed the proof. Well, I managed the proof of most of it, and then it managed the proof of the first 64 cases. And then during this, while I was writing this paper, we ended up refactoring the algorithm and everything for base 10, among other things. And it has since been used for this proof that the logarithm of 2 is less than this rational approximation of it, which we needed for the birthday problem. And then it also gets used in a couple other places. So one question you can ask is, why is it that we managed to go so long without ever having any numbers bigger than like 8? It's abstract math mostly. You know, in order to prove that, I don't know, some group theory facts or other things, you almost never have to deal with big numbers. I think we checked and found that Fermat's last theorem doesn't even use any numbers bigger than 12. It's one of those strange facts that abstract math never needs numbers. So, but now we have numbers in the rare cases when we really need to deal with numbers bigger than 10. And once we get into bigger computer proofs and things, this becomes a bigger issue. We have to really handle large numbers, large computations and things. So it's important to have something like this. This is pretty much the first true full theorem prover, at least for a limited domain. We do have previous work for step provers, which can show 1 step out or 3 steps out. But this is the first time, at least that I'm aware of, where you can calculate the entire proof for a given fact in a limited domain of fact. So much more is planned. We really want to extend this capability to more kinds of problems. I want to look at automating conversions from whole light. There's already an algorithm for doing this, and we just need to have it implemented in the computer. So hopefully we'll be able to get this with a new planned infrastructure for doing user scripts of this form. So FlySpec, I think many of you know that FlySpec is a big project with Tom Hales, formalized in Whole Light and Isabelle. And it's reasonable to ask the question of whether you can get FlySpec into Metamath. And the answer is pretty much no, not right now. A Metamath proof can be verified in linear time or maybe n log n, but the proofs are a lot longer than what you'd see in an Isabelle proof or a whole light proof. The length of a Metamath proof would be proportional to the running time of a whole light proof. So if a whole light proof is going to take weeks, then it's probably going to be very long in Metamath. So just a little bit to close here, how do you optimize for Metamath proofs? Don't search. You already know the answers. Here's a nice way to say it. Metamath can prove NP-hard problems. Of course, it's not magic. You have to do the NP-hard work at the beginning, but you do it once. You store the witness, and the witness is much smaller. And this isn't anything new or unique to Metamath. It's just that Metamath has a sort of culture of doing this, of having the shortest actual witness proofs. You spend more time finding the answer, making your proof as short as possible in order to make the verification of the full library quick. The verification of the entire set.mm file is about 8 seconds, which does not compare to the verification times of almost every other proof assistant which I'm aware of on a similar size, which are generally on the order of like weeks or hours or something. So yeah, spend more time making your proofs as short as you can. And let me show you what the actual, so this is the oh, no, you're not seeing it. Okay. So this, you still can't see. Okay. There we go. So here's the actual algorithm. I attempted to put pieces of this in the paper, but I think I just confused the reviewers. So if you want to, you can just email me and I will give you this, and it's also on the Metamath website, I believe. So yeah, this is the algorithm, and it's very nice. And here is you can see here there's cases based on all the different shapes of expressions. I like the fact that the Mathematic pattern matching can handle, you just check based on the form of the expression, are you going to apply this theorem or are you going to apply that theorem? And so all the different cases, and there's many more cases here than are strictly necessary. Many of these are to make the proofs more efficient. So having more special cases is helpful for that. And yeah.
Any questions?
So when you measure the brain index, do you count the number of lines or the number of characters?
I'm not sure what you're referring to.
Okay, last time you said that you had a very short, you were surprised because your formalization is quite short compared to,
Mm-hmm.
Okay, so you didn't say that this time, but
Oh yeah. So when I was measuring that, that was the number. I guess it would be mostly the number of lines. Although I was also counting the length of the labels. So the labels have roughly constant length, so that's not.
Okay.
It's roughly proportional to the number of lines.
Because if we look at that file, lines are quite big.
Oh yes. We go back to. Okay, so you're referring to these formulas here. So these formulas actually do not have to be typed by the person formalizing the proof. These can be automatically generated from the theorem references,
Okay, so
as well as vice versa. You can also just type in these, and the theorem references can be discovered. So when measuring the de Bruijn factor, we actually just counted basically the amount of text in that column, as well as the references, because those are important.
So, not quite sure whether I've understood what you have done. So you have proved these things that you said originally Erdős had to say let's n be greater than 4,000 and had to prove all these cases before.
Yeah.
So you did that, and then you also did the proof for if n is greater than.
Oh yes, of
Right,
course.
but you
Actually,
didn't show-
the hard part was actually the n greater than 4,000.
I would have thought so.
Yes,
Right.
yes. But this, but the fact that there were 4,000 was daunting when we began the project. It was.
Yes.
There's also this giant computation we have to do, and how do we handle it? And so this project came out of how do we handle it.
Right. So you presented mainly now how to do all these computations
Yes.
in order to get these cases,
Yes.
and you didn't really show us all the other proof. So is that difficult to understand? Would you also get that out of your system then?
The n greater than 4,000 proof is an abstract math proof. It doesn't depend too much on this.
Right.
It was mainly the motivation for this research.
I see.
So, yeah. Yes.
I'm just curious about the phi spec stuff. Is that settled now? Is it a theorem?
Oh no, certainly not.
It's not?
Not in Metamath, no.
No, I mean.
In general, it is, yes.
It is.
The
Oh,
project's finished.
yes, the project has finished,
So
yes.
why is it referred to as still as a conjecture?
Why is Bertrand's postulate still a postulate? It's been proven for 150 years.
Oh, it's just historical?
I think so, yeah.
Kepler's theorem.
It's Kepler's theorem. Okay, all right.
Give us an indication, if you now were to use some other computational structures, permutations for instance, how do you think, how difficult would that be to get into Metamath?
To get
Permutations, right?
permutations?
Permutation groups, you know, say you want a
Um,
sieving proof where you want to show that a particular permutation is not generated by one group, something like this. How difficult would that be to get these kind of structures in there?
I can't answer that question mostly because I don't know the general techniques for solving it. But I imagine that given an algorithm for solving it, you would be able to produce a Metamath proof whose steps are the same length as the order of the algorithm.
Right, okay. That would be interesting.
Right.
All right. There are no other questions. Thank you very much.